Hi, my name is Tom Brown. I'm the Director of Borderland Sciences Research Foundation, and here we are back again in our secret lab hidden in the vast suburban wastelands of Southern California. Today we're with scientist Eric Dollard, who's going to explain to us longitudinal electric waveforms. Now, the modernistic science of today will tell you that longitudinal electric waveforms do not exist, and we're going to show you that they do. And here, basically, to get a practical demonstration or a practical analogy, we have water, and everybody understands the waves in water, which we can call a transverse waveform, standard waveform. And we know standard waves as they go along in the water, and the movement of the water is up and down, just like we know a boat on the water will go up and down, and the energy flow goes in this direction. So a transverse wave, we have a phase quadrature between the movement and the energy flow. And here we have longitudinal waves. And a longitudinal wave could be like a tidal wave or a tsunami, which we know is undetectable until it hits the shore. So as it goes through the water, the movement of the water is linear and the energy flow is linear, so we see it's in phase conjunction. In the direction it goes in, the boat on the top will receive no up and down motion from that wave. And to get a more practical demonstration here, Eric Dollard will demonstrate. We have here a piece of BX cable, and I'll just act as the ground on this.
Okay, to start with, our transverse wave, which will be our quadrature motion, will be represented by this form. We can see, have an exact analogy to what's drawn on the board. If I transmit just one pulse, you can kind of see it takes a long time to get to the other end. But the longitudinal wave, of course, is over there almost immediately, and other than the slippage at the other end, it's almost undetectable that this wave even exists, other than that little shaking around. But it's slower. There we go. See, there's really not much motion up and down or around, but it's there right away. As soon as I move my hand, the other end responds. Where in this case, it takes a very long time to get there. So this serves as a very practical analogy of these two types of waves. Okay, as to carry our analogy further here, if we drop a stone in the water, we'll produce both types of waveforms in the water. Now we know the transverse waves form concentric rings which propagate out. But the longitudinal waves, which are not normally seen, of course, travel as straight lines in the depths of the water, which are indicated by down this way. Now this also happens to be the electric field around one wire, or what's called electrical conductor. Now if we look over in the other page here, we see when we start having a system of conductors, then the field changes, and we can have either the transverse motion of electrical energy, which moves into the paper, or in other words in the directions of the wires, which these are being the cross sections of the wires, or in a transformer, energy is conveyed longitudinally from primary to secondary conductors. So we have again our two types of fields here, representing longitudinal and the transverse, which of course is hard to represent because it goes into the paper. And again, these things are at right angles to each other. The longitudinal is going that way and the transverse is going this way. Okay, these lines that we see on the paper that we've represented as our wave fronts, in actuality around this system of conductors, represent what are called the dielectric fields of induction and the magnetic field of inductions. Now in general, the magnetic fields of induction are concentric rings, as indicated by the dark lines here. Dielectric field of induction are usually radial lines, as indicated by the dotted lines. So in general, the dielectric field is conducive to the transmission of longitudinal forms of energy, and the magnetic fields are conducive to the transmission of electromagnetic or transverse forms of energy. So we might say that our transverse waves are called electromagnetic waves, which has become the standard terminology, but our new waves, or longitudinal waves that we're dealing with here, are called longitudinal magnetodielectric waves, in contradistinction to the existing form of the electromagnetic or transverse electromagnetic waves. This book by Steinmetz here is a good source of reference to prepare one for the study of these types of electric induction. Here's the title page here for those who'd be interested in finding out more about this stuff. This book is quite old.
1914.
It's written as an explanation for another book that Steinmetz wrote on the theory of electric waves, which is extremely complicated. But this one's quite simple and will render information to the electrical engineer that completely change the outlook on electricity. In our study of electric waves, we're going to start with the well-understood transverse electromagnetic wave, and we're going to do some measurements here to determine the characteristics of such waves. To start with, we'll have a radio frequency generator and a step-down transformer to drive a long section of coaxial cable, and then a high impedance bridging voltmeter to measure the rise of electric potential due to resonance at the distant end of the cable. Now we'll go over to our test setup here on the bench. And we have our radio frequency generator and our transformer, which is a little toroidal core inductance. And then we have a roll of just regular coaxial cable and the high impedance voltmeter. Now what's going to happen here is a series of impulses, alternating electric impulses, will be produced by the radio frequency oscillator and launched down the cable with a finite propagation velocity. These impulses will travel around in the cable, reach the open circuit at the end of the cable, turn upside down, and reflect back, and again be delayed and return to the oscillator. When the impulses of the oscillator frequency are such that they match the time of propagation delay produced by the propagation of electricity down the cable, when this inverted impulse comes back from reflection, the oscillator has gone through 1/2 of a cycle, and it also is producing an inverted impulse. So these two inverted impulses add, and a double impulse goes back down the cable, turns right side up when it gets reflected, comes back to the oscillator. The oscillator has gone through another 180 degrees of shift and is producing a right side up impulse to match the reflected inverted or now right side impulse. And this process keeps on going on until the voltage rises to a level where the losses of the system prevent any further increase. So what we're going to do is we're going to sweep the frequency here and find the resonance point of this cable to determine propagating velocity. Now, as you can see on the voltmeter here, we have a definite peak. So I'm swinging an oscillator. If we go to roughly our half voltage points, we find we have a bandwidth of about a few hundred kilocycles roughly. And it peaks out at a frequency of almost precisely 2200 and 20 kilocycles. So what we'll do next is we'll plug this into our equations and determine the speed at which our impulses propagate on the coaxial cable. In reviewing our test data for our transverse electromagnetic wave of electric induction for a TEM coaxial cable RG62, which is the cable type we use, transmission impedance 93 ohms, total length of cable 2,750 centimeters. Full wavelength of this piece of cable then would be 11,000 centimeters, since it's a quarter wave resonance and you have to multiply the length by a factor of 4. Now, based on the velocity of light, frequency of quarter wave resonance for a propagating velocity equaling that of light, the frequency should come out to 2727 kilocycles per second. The actual frequency we measured was 2,220 kilocycles a second. Now if we take the ratio of these two velocities, we find that the propagating velocity along this cable was 81% of the velocity of light. Hence, this transverse electromagnetic wave is a retarded wave in that it propagates at a velocity less than that of light. Now, the reason for this retarded propagation velocity is due to the fact that the velocity of light is slowed down by the translucent medium that fills the cable to insulate it, and the resistive losses and conductive losses of the cable in general also tend to slow down the wave a little bit. Now what we're going to do next is go to the longitudinal wave and show our test setup, do our measurements, and perform our calculations on this wave. Okay, now we have our longitudinal wave test set up. Again, we have the same generator. This time our transformer couples the generator energy to the first turn of the coil, which is wound of very fine, fairly fine wire. And then we have a capacitive probe pickup to measure the voltage rise at the end of this coil. And at the neutral end of the coil, we have a large capacitance plate to produce our impedance dissimilarity, so we end up with a quarter wavelength rather than a half wavelength resonance on this coil. Now we'll look at our test setup again here. And we have, of course, the same generator as before. And then focusing in on the coil here, we see we have a primary turn, which loosely couples to the secondary, or the actual coil itself, through the first turn here, and then the rest of the coil pretty much engages in a free oscillation. And then our capacitive pickup is just a clip lead clipped on to the so-called insulating part of the coil. So we have a very light coupling between the end turns here and the probe wire, which of course goes to our same voltmeter. So what we'll do is we'll sweep around with the oscillator again and find out what kind of resonance characteristic we have here. Now we notice a difference right away. The resonance of this type of wave is much sharper. Rather than varying over several hundred kilocycles, now I'm varying over several kilocycles. So we're talking about a sharpness factor, or a Q, of 100 times greater. Now our frequency lands roughly 3,400. We're in between two marks on the dial here. We'll say 3,400 kilocycles per second. Now we'll go to our mathematics and compare this with the other wave and get into our velocities and frequencies and what have you, so we can study the character of this wave. Okay, covering the test data here for a longitudinal magnetodielectric wave, our LMD wave structure was a Tesla extra coil. Transmission impedance of this was 4,200 ohms. Wire length, again, is 2750 centimeters to make it analogous to our roll of coaxial cable. And again, the full wavelength would be 11,000 centimeters. 4 times 2750. So the frequency of quarter wave resonance for a propagating velocity of this length equaling to that of light would be 2727 kilocycles, such as before. Our actual frequency measured, of course, was 3,400 kilocycles per second. So taking our ratio of frequencies or velocities gives us a velocity of 126% of the velocity of light. Hence, this wave is an accelerated wave. So we've broken the speed limit of the velocity of light. Or you might say we might get a ticket from the relativity police in this case. At any rate, going back to our structure over here, we can see how this occurred. Is we're really not having transverse flow between the turns anymore, but the energy is now spiraling due to the complex quantities of induction along the wires in this direction. So we have a spiraling wave around the coil, and this gives us